So to start off today, we are looking again at conditional GANs, text-to-image synthesis. So to start off, just as a reminder, we are trying to generate images based on a text description. And this is our architecture. And I'd like you to turn to the person next to you and try to explain what you would think. So as a reminder, this is like a normal GAN architecture. We have a generator on the left side and a discriminator on the right. And our generator takes as input a Z vector sampled from a standard normal distribution, as well as an embedding of a text prompt. Then our discriminator takes as input an image as usual, as well, and it also takes as input the embedding of a text prompt. Now, if we were to have this set up, and so this is what I'd like you to explain to the person next to you. What do you think would happen if we did not include this text prompt in the discriminator? And this is a discussion question, so talk amongst yourselves to. Okay, what do you think would happen? Let's hear what you think. What do you think would happen if we excluded this text embedding from the discriminator? Yeah, Dane, what do you think? Yeah, the thought is that we would end up generating images without text that maybe look realistic, but which do not reflect a text prompt. And I would tend to think the same thing, because if you remember, the purpose of the discriminator is to tell whether the image generated is real or fake, and whether the text prompt matches the description or matches the content of the image. Any questions on that? Yeah, Cole. Good question. So the question is whether it compares the embedding of the image to the embedding of the text. I don't think it does so explicitly. However, it probably does something very similar to that implicitly. And that's actually a really interesting idea to, if you wanted to try that for yourself for a final project or something. Yeah, try a conditional GAN where the score for the image is based on the dot products. The score for whether the image is real is based on, or it matches the description, is based on the dot product similarity with that text embedding. Yeah, that's a very interesting idea. Okay, so here's our algorithm. And I wasn't sure that line 12 was correct last time. After class, I looked at it and I convinced myself that it was correct. So if we remember, the SR, the discriminator predicts 1 if it believes that the image is real and matches the text, and 0 if the image is fake or if it doesn't match the text. So with that in mind, turn to your neighbor and see if you can explain why we want the generator to maximize log S of F. Okay, so as a reminder, S sub F is the discriminator score for fake image right text. So with that in mind, why do you think we want our generator to maximize log S of F? Thoughts? Yeah, Max, you want to take a shot? Yeah, so as a reminder, maximizing log probability is the same as maximizing probability. The maximizers occur at the same point. So that the log is just for numerics. And then, yeah, totally. So S of F is high when the discriminator takes as input a fake image and right text and the correct text, and it thinks that it is the real image corresponding to the text. So that is the case. S sub F equals 1 is when our generator is successfully fooling our discriminator. Any questions on why that is our objective for the generator? All right. Okay, moving on. And then, so I'll just make a comment here. So this is a conditional GAN for text to image, but you can also imagine conditional GANs for image to image. And a couple of students are doing projects with that type of GAN. If that's the case, then any ideas what you might choose for your architecture? Here we have a basically the second half of a U-net going from our Z vector to that image. Any thoughts on yeah, what kind of architecture we would like if we were conditioning on an image here? Yeah, what do you think? Excellent. Yeah, I think that's a great idea. So you're saying that this phi function would, instead of being an RNN or a transformer for text, we would have a CNN or something like that, creating an embedding of our image, which we would then use in the same way. I think, yeah, that's a pretty good idea of how you might do this for images. All right, so just a quick look at the results. So these are zero-shot generated bird images, meaning that we are conditioning on text that the network has not been trained on. And so we have an all-black bird with a distinct, thick, rounded bill. And this is the true image above, and then the generated images are below. So you can see we're getting things that look like black birds, maybe containing black bills, perhaps. The small bird has a yellow breast, black crown, and black superciliary. I'm not sure what that is. Anyone know what a superciliary is? Well, I'm not sure we can evaluate on that one, but looks like we're getting some yellows. That bird definitely has a yellow breast and a brown crown. So starting to see some ability to influence these generated images based on text. Okay, so this is similar generated flower images. These flowers have petals that start off white in color and end in dark purple towards the tips. It looks like it got a bit confused on the ordering because it looks like some of these are white on the outside and purple towards the middle. But generally getting the colors right, doing a decent job. And we'll skip over that one. This is kind of an interesting one. So if you remember, the input to our generator consisted of two parts, a z vector and a text embedding. So here we are taking the same z vector and just changing the text embedding. And this is the result. So on the different rows in this figure are different text prompts, and then the different columns are different z vectors. And so you can see that, yeah, we have the yellow breast with gray features and a small beak all across the top row, but the style tends to match more the image above than the images across. And so this is kind of an interesting approach to style transfer using text conditional GANs. Yeah, what patterns do you notice about what is captured in the style of these images? Or really you can think of it in the z vector. Yeah, Tim, what do you see? Interesting. So you're noticing that the image controls, yeah, the direction that the bird is facing. Totally, yeah. So we have this, all of these images are facing to the right, except the one on the farthest right. And you can see that every single generated bird is facing the opposite way. Very interesting, yeah. What else? What else seems to be captured in the z vector? Yeah, Joseph? Interesting, yeah. So you're saying the greens and the background, and then also a little bit of the foreground in like the branch that it's sitting on. Why do you think that information is getting captured in the Z space and not other information? For example, why isn't the color of the bird or yeah, what do you think it is that's causing these features of which way the bird is facing and the background versus other features to be captured in the Z space? I might even venture to guess that you could not find a single feature that tends to be described in text descriptions in this Z space. Can you think of why that might be? Yeah. Interesting thought. Yeah, so the thought is that these features are probably more consistent across the training data. Totally. And I would say that would be a reason why we have like, yeah, background and like, yeah, background color and like tree branch instead of very specific background details like, I'm trying to think like, I don't know, a guy with a lawnmower or something, just because, yeah, the Z space tends to capture the most salient features. I would also say that like, if we were to train a normal GAN on this, I would expect the Z space to include features like color and type of beak and size of bird. But my guess is that because when we train this GAN, we provide that information in the text description, those features are contained in the text part of the embedding, and then all of the features that are contained in the Z space are not related to features that showed up in the text description. Does that kind of make sense? Yeah, so the idea is that because we are providing information about bird size and color and characteristics about the bird in our text description, because that information is provided there, it becomes excluded from the Z space. And so basically the text embedding comes to capture the features that describe the bird, and then the Z space comes to represent all of the other axes of variation that occur in these photos. Any thoughts or questions on that? Yeah, Cole. Interesting. Yeah. So the question is, how would the Z space be affected if you made more descriptive? Yeah, if you became more descriptive and described the background and what the bird was standing on in your text description. I'm going to turn that back to you. What do you think? What do you think the Z space would capture then? Totally. I think that's a very good guess at what would happen, that it would be either become less and less relevant, or it would pick up on like finer grained details, like the guy with the lawnmower in the background or whatever. I mean, these don't have the resolution for that, but you get the point, the kind of less salient features. Yeah, good question. Okay, so here we have interpolating in text space. So this is kind of interesting. So we take the embedding for one text description, and then the embedding for another text description, and then we take we'll call this V1 bluebird with black beak, and V2 will be red bird with black beak. And we'll take, on the left hand side is bluebird with black beak, and then on the right hand side is red bird with black beak. So V1 on the left and V2 on the right, and then the images in between are we'll say like 0.25 times V1 or 0.75 times V1 plus 0.25 times V2, 0.5 times V1 plus 0.5 times V2, and then 0.25 times V1 plus 0.75 times V2. And so everything else remains the same. We keep the same Z vector. All we're changing is the text embedding, and we see the smooth transition between the generated images. Does that make sense? Okay, and then similar thing, we have a small bluebird with black wings becoming a small yellow bird with black wings, and you can see the smooth interpolation. So this is a good way to kind of visualize what these interpolation ideas are good ways to visualize what your network is learning. And basically, if you have a well-trained GAN, if you have a poorly trained GAN, you will basically see something that looks like pixel-wise interpolation, where all of the intermediate images look blurry. But if you have a well-trained GAN, you will see a smooth transition where all of the intermediate pictures look fairly realistic. Okay, any questions on how interpolation works, or how we got this figure? All right. Okay, so then we're gonna take a look at some results. So yeah, any ideas what the text conditioning of some of these might be? Kind of bad looking images, huh? This one definitely looks like a dog, but then these might be a tarantula, maybe. This one might be a monkey, maybe some sort of bird, a corgi or something. You can see some issues starting to arise with some of these generated images. Again, these are pretty high resolution generated images, but we're seeing some kind of weird artifacts. What kinds of things are you noticing about these generated images? It likes eyes, yes. Maybe a little too much. Yeah, what else? Let's be generous. What do you see that this GAN doing fairly well? Yeah, what do you see? Totally. That is, I mean, there were no right answers, but that was that's what I noticed, and that was kind of what I was looking for. Yeah, so we're seeing it actually does pretty well at fine grained details. Like if you zoomed in on any part of these images, they might look all right. You know, you might see a little corner of a monkey face or the corner of a dog face or a dog's nose. Yeah, but when it comes to global coherence, these GANs tend to struggle. Okay. Yeah, and also, yeah, counting is kind of a subset of those problems where you have multiple, like 6 legs or 7 eyes in the global image. So that counting is one instance of a global problem. Perspective. So again, it looks like we have one angle of a dog on the right side of the picture and then a different angle on the left side. And yeah, more global structure issues. So GANs are far from perfect. If you tune them right, you can get some really good looking images or whatever you're trying to generate, but there are some very systematic problems that you tend to see in GANs. This is another one of those problems, which we will call mode collapse. So this is a case where we are trying to model a 2-dimensional distribution. This is called a mixture of Gaussians. So this distribution is made up of 8 like sub-Gaussian distributions. And we're going to try to train a GAN to learn it. So ideally, we would start out with some initialized distribution, explore around in space a little bit, anneal to something that looks like kind of circle around that hits all the modes of this distribution, and then eventually converging on in tight clusters around each of these modes. And you can think of each of these modes as representing different classes. So if we were to generate images of animals, you can imagine one of these modes would refer to cats, another would be dogs, another would be horses, etc. If we were to be just looking at pictures of dogs, these could be Irish setters, these could be golden retrievers, black labs, etc. So when we're talking about modes, we're talking about different parts of the distribution that there tend to be clusters in. So yeah, GANs take a lot of tuning, a couple of like, I guess, hacky tricks to make them work. Use strided convolutions instead of pooling layers in the discriminator, and use transpose convolutions in the generator. Use batch norm, remove fully connected hidden layers for deeper architectures. Use ReLU in the generator and leaky ReLU in the discriminator. Yeah, and these are just kind of things that they found through experimentation seem to be useful without any great theoretical explanation why. Yeah, Max. It's definitely not just a discriminator problem, because if you think about it, like we want our generator to be generating a diverse range of examples. And so, but you can imagine, like, I guess, knowing what you do about GANs and how they are trained, why do you think mode collapse might be a problem? Like, why do you think that would be a failing of GANs based on the loss function that we have? And this is for the class. What do you think? If you remember, our generator does well if it fools the discriminator. Doesn't matter if the generator, is there anything in our loss function that tells our generator that it needs to generate a very diverse set of examples? No, not necessarily. It could just be generating over and over, basically this it just gets really good at generating this super realistic picture of a mountain or something. And that could be one way to fool the discriminator. So yeah, that's kind of an idea, a hint at where this mode collapse problem might be coming from. Yeah. So yeah, a couple of other issues with GANs. It's really hard to interpret the loss curves because you have the generator training, then the discriminator training, and they're kind of trading off, and both of them can be getting better, but the loss doesn't really go down because while one is getting better at discriminating, the other is getting better at fooling it. There's this problem of oscillating training. So because we alternate between the discriminator and generator, you can end up actually getting worse with both of them for that same reason of having meaningless loss curves. And this is actually due to some fundamental mathematical issues with the GAN loss function. And then, yeah, another problem being vanishing gradients, where your discriminator just gets too good, and so you don't have any kind of gradient signal for the generator. So there is an entire lecture that we have that talks about how to handle these problems in practice. That talks specifically about the math of non-conservative vector fields and some things that we can introduce to the loss to fix this problem, fix the problems of mode collapse. However, we are dropping the GAN lab that was originally in this class in favor of a diffusion lab. And so in practice, you are in this class not going to have to necessarily deal with the difficulties of training GANs. And one of the reasons for this is because even with all of the improvements that exist, it was really hard for students to get quality looking results on the GANs. And so we really want you to be able to have something like, yeah, to be able to train a network that performs pretty well, which is why we're going with diffusion models. And so if you're interested in the math of these problems and some approaches that people have taken to fix them, I'm going to post the slides for the lecture that we would have had on that subject on Learning Suite, and you can explore those on your own time. Okay. Yeah, and these are this is a hint. This slide provides a couple of hints at where that lecture is going. Okay, so any questions on our conditional GANs or on failure modes of GANs before we end this lecture? Okay. Okay, so there is a vast landscape of GANs that have been developed since GANs were originally introduced in 2014. We took a look at the deep convolutional GAN, the original GAN, and today we're going to look at style GAN and big GAN. These are, yeah, two particular architectural adaptations that have gotten really good results. So let's take a look. So this is big GAN, and the main takeaways from it are that bigger is better, and also worse in some ways. But basically, the goal of this paper was to generate very high resolution, high fidelity images. So these are some samples from big GAN. How do these look compared to the samples we were seeing before? Quite a bit better, huh? Yeah. So yeah, these are class conditional samples. So yeah, we got a hamburger, a butterfly, an island. What kind of dog is that? Oh no. Yeah, so yeah, looking pretty good. Some more samples. And you can see that we're seeming to do a lot better. Yeah, I guess, what do you think, see these images doing well and compared to the previous GAN we looked at, and what things still seem to be an issue? Yeah, what do you see? Totally, global cohesiveness. Yeah, we can see the ears are in the right place with respect to the eyes and the nose and the mouth. Yeah, totally. Yeah.
Generally, not one pocket on the.
Yeah, struggling with regularity a little bit. Yeah, interesting. I'm still noticing a couple of issues with, like, you look at the head of this wolf and it looks excellent, but then you go below the torso and it looks like it's really struggling with the legs still. So yeah, we're seeing some improvement. Well, a lot of improvement. Still some difficulties though. Okay, so we're going to be talking about some metrics that this paper introduced to evaluate GANs on some of these problems that GANs tend to be subject to, specifically mode collapse. So we're going to have two objectives. One is saliency. So basically, how well an image represents a particular class, and then two, diversity. So as opposed to, yeah, this is to measure how well our model avoids mode collapse. Can we generate rocket ships and mushrooms and dogs and bubbles and things like that? And so we're going to wrap all these two objectives in a single metric called inception score. And so for inception score, higher is better. The previous best conditional GAN had an inception score of 52.5, whereas big GAN gets 166 and real images get 233. Let's look in the math. So here's how we're going to define saliency. Saliency we will define probabilistically as P of y given x. Basically, we want P of y given x to be large. We want, given a class, we should, let's see. Sorry, given an image, the score for one particular class should be very high. So we want to maximize, we're not going to specify which class it is, but we want to, we want to have a high probability of that class. Diversity, on the other hand, we're going to express as P of y. And if we want diversity, how do you think we can, what do you think we want some characteristics of y to be if we want, or P of y, what do we want P of y to look like if we want a wide diversity? Remember that y is the class. So if we were to sum over all images in our data set, would we want P of y to be, or sum over all generated images? Would we want them all to be in one class, or would we want them to be in many classes? Many classes, right? That would be diversity. And so that's what we're going to do. We're going to bring this all together and say that P of y is the sum over all generated images of the probability of the image times the probability of class given image. So this is just, so the form on the right hand side of this summation, this is equal to the joint probability of y and x, P of x comma y. And we can split that as P of x times P of y given x. And then if we sum over x, we can get the marginal P of Y. And so what this will look like is we're going to plop that in to this equation here for inception score. We are going to try to maximize the KL divergence between probability of Y given X and probability of Y. So and again, one more time, P of Y is the probability, the raw probability of the class across all generated images. And P of Y given X is the probability of the class for one particular generated image. All right, so let's look at some examples. So what happens if P of Y and P of Y is low and P of Y given X is high? What will the KL divergence between, what would the difference between those be? Yeah, Max? That's right. We have not talked about KL divergence in this class. That is actually in the lecture that we dropped on GANs, but it should probably introduce. KL divergence is basically a measure of difference between distributions. Yeah. In fact, let's not focus too much on that, just because we haven't discussed that particular concept. But basically, the goal is to have our probability spread evenly across all classes for our generated images, but that for any particular image, we want the probability of its class to be high. Okay, any ideas what we might use as a model for P of Y given X? I'll give you a hint, it's not part of our GAN. We're going to have to use a separate deep learning model to calculate this inception score. Can you think of a type of model that takes as input an image and predicts classes for those images? What was that? Yeah, so that a unit does pixel by pixel classification. We could just use a normal CNN in this case because we're just trying to classify the entire image. So P of Y given X will be given by CNN. And in fact, they often use a CNN called the inception network. And yeah, so we'll use an inception network to predict the probability of a class given our image and use that to calculate the inception score. Any questions on inception score? All right, so inception score is good, but it's not perfect. And the reason for that is because inception score doesn't say anything about how the distribution of generated images compares to the actual distribution over images. And so a couple years later, researchers introduced this other metric called Fréchet inception distance. And the idea is that we want something similar to inception score, but which also measures how well we match a given distribution over images. And it's given by this kind of complicated formula up here, which we are not going to try to explain because it comes from something else different from this, and then it can be shown to be equivalent to this kind of complicated formula up top. But I think that this algorithm makes a lot more sense. So the way the algorithm works for calculating Fréchet inception distance is as follows. We are going to take a function from the space of images to Rn, And we're going to call that, we're going to make that an inception model. So this is just, so F is just a CNN that takes input as input images and maps them to some embedding space. Then we're going to take two data sets, and one of those data sets will be our a true data set, and the other data set will be generated images. And then we're going to use our network to extract features from both of these data sets. And then we will, so we now have basically converted each of these data sets to vectors in a 2048 dimensional space. And then we're just going to fit two Gaussian distributions, like using maximum likelihood, just normal classical statistics. And we're going to fit these two Gaussian distributions for each of those embedded images. And then and actually, I do not remember what DF is. However, it's basically, I'm guessing it's something like KL divergence between these two Gaussian distributions. So if we were to sum it up, yeah, can someone try to explain that algorithm back to me in their own words? Okay, let's try this one more time. So we're going to take a CNN and take a data set of true images and generated images. We're going to use the CNN to convert each of those data sets into feature vectors in feature space. Then fit a Gaussian distribution for each of those distributions, and then see how well they overlap with each other. Seeing a few more nods. Drake, you want to try explain this in your own words? So I'm going to pause you there. We're actually not getting a vector of labels. We're getting embedding vectors. So this is going to be like the second to last layer output of the neural network. But yeah, continue. Totally. Yeah. Yeah, exactly. And so yeah, we have a question on that. Totally. Yeah, totally. Yeah, I think that's a great analogy. Okay, so that is Fréchet inception distance. So now with that in mind, these are some scores on some Fréchet information or Fréchet inception distance in the second to last column, an inception score in the right column. The right column, higher is better. Left column, lower is better. And so you can see we have different sizes from top to bottom, and we also have including specific features of the network. So yeah, so some trends that you should notice are that as we get bigger, our scores get better. Yeah, what other trends do you notice on this table of results? Yeah, Joseph? Good question. Yeah, so these are three particular innovations of Big GAN. So one of the issues that they saw when they scaled up training was that basically catastrophic forgetting where the loss would suddenly go up really high and never recover. So to remedy that, they included this orthogonal regularization, which basically enforces that each weight layer is orthogonal at each step of training. Yet that the rows in each weight layer are orthogonal. Skip Z is including skip connections. So yeah, specifically from the latent space to multiple layers throughout the network. And then shared, I'm actually not sure what the shared embedding refers to. It may be a shared embedding between the Frechet and inception distance network as well as the discriminator. Yeah, but you can see that as we add each of those, our Frechet inception distance goes down and our inception score increases. So all of those help quite a bit. Okay, so this is looking at nearest neighbors in feature space. So this is the feature space of a CNN of this generated image. You can see, and these are the top left is the generated image, and all other images are images from the training data set. You see any image that looks relatively similar to the training image? Yeah, maybe this middle left one, but even that one seems quite a bit different to me. And so the purpose of this is to show that these generated images are perceptually significantly different from anything that the network has seen before. This is similar, but in pixel space instead of embedding space. Again, you don't see any image that looks like an exact replica of this generated dog. And so this is kind of a sign that our network is doing decently well at avoiding mode collapse. Okay. Oh, and actually, sorry, this is also feature space. This next one is pixel space.